Okay, in the following several videos, we discuss the exercise for integral. I posted maybe 2 weeks ago. Uh, now, we consider the first problem. Suppose A, B, C are real numbers, not all zero. At least one of them is not zero. And kappa is the norm of this vector ABC. Kappa. And f is a continuous function. In the interval minus kappa. Then the integral over the unit sphere of this function this is the surface integral. The conclusion is that this equals 2 pi minus 1 f kappa u du. The surface integral is converted to a definite integral. Okay, so how to solve this problem? So this is the sphere, and ABC is a direction. ABC, and we are required to compute the integral of this function of x, y, z. This is a composition of ax plus u equal to ax plus by plus cz, and composed with the single variable function f. How to compute this? The idea is that we rotate the coordinate system so that in the new coordinate system, ax plus by plus cz is a single variable. Okay, so and can we rotate the coordinate system? This is equivalent to making orthogonal transformation. Okay, and in our previous study, we have an example saying that the surface integral is invariant under the orthogonal transformation. Using this result, we can rotate our coordinate system. So to prove this result, we take a orthogonal transformation. That is T. This transformation, the new coordinate is xi eta zeta, which is the first. We don't care about these entries of the orthogonal matrix, but the last row we require it to be A kappa, B kappa, C kappa, and then X, Y, Z. Here kappa is not zero because A, B, C are not all zero. At least one of them is not zero. Therefore, kappa is not zero. So this orthogonal transformation makes sense. Why we need to divide by kappa here? Because every row vector of an orthogonal matrix, the norm is 1. So you need to normalize the vector ABC so that the resulting normalized vector can be a row vector of an orthogonal matrix. Okay. Then under this transformation, our integral is f ax plus by plus cz. under this orthogonal transformation, the sphere, the unit sphere, that is the boundary of the unit ball, is transformed into itself. Therefore, the image surface is still the unit sphere. And ax plus by plus cz is f kappa zeta. Okay. By the definition of this transformation, we know that zeta is kappa ax plus kappa by plus kappa cz. Therefore, ax plus by plus cz is kappa zeta. So in this step, we have used the result we proved previously. That is example 2.21 in the lecture notes. Okay, applying the result in example 2.21 to the inverse transformation of t. That is t inverse. We've obtained this result. Okay, you can compare the conclusion of that example and the situation here. Now, next we need to compute this surface integral on the right hand side. Then we take a parametrization of the sphere. Parametrization of the sphere is that xi eta zeta is sine phi cosine theta, sine phi sine theta cosine phi, and phi theta belongs to the maybe I will write theta phi. Theta phi belongs to the rectangle 0 to pi cos 0 pi. This is the parametrization of the sphere. Okay, then we use this parametrization of the sphere to compute this surface integral. The surface element under this parametrization of the surface is that we know that the sigma is sine phi d phi. You can compute, you know that the surface element is sine phi d phi. Because this is the vector valued function r, then you compute r phi cross maybe r theta cross r phi, then take the norm. Then oh sorry, I have a d theta missing here. Okay, then this is the vector between the surface element over the sphere and the area element of the phi theta plane. That is the d theta d phi here. Okay, so using this parametrization, you can transform the surface integral on the right hand side to be not double integral over the rectangle of the parameters, that is 0 to pi cos 0 pi. Then f kappa zeta is what? Zeta is cosine phi. By our parametrization, zeta is cosine phi. Okay, so cosine phi. Then d sigma is sine phi d phi. Okay. Then this double integral computed by iterated integral. So we integrate over theta. Theta is 2 pi. Then for phi is 0 to pi. F kappa cosine phi. Then sine phi d phi. So the inner integral does not depend on theta. Therefore, the outer integral for d theta from 0 to 2 pi can be simply write 2 pi. Okay, so we have this equal 2 pi 0 pi f kappa cosine phi sine phi d phi, and this sine phi d phi is exactly d cosine phi. So introducing a change of variable, u equal to cosine phi. Making the change of variable u equal cosine phi. So this integral will become 2 pi. So this is from 1. U equal to cosine phi. When phi is 0, u is 1. When phi is pi, u is minus 1. And the function is f kappa u. Sine phi d phi is minus d cosine phi, so it is minus d du. Minus. The minus sign will, maybe I will write minus 1 du. This minus 1 will use to switch the upper limit and the lower limit of this definite integral. And at this point, you obtain the right hand side of the equality we want to prove. And this complete the proof of this proposition. This problem. Okay. Now we consider the second problem. The second problem, as before, kappa is the square root of a square plus b square plus c square is not 0. And the f is a continuous function minus kappa. Then we want to solve triple integral over the unit ball of this function ax plus by plus cz over the square root of x square plus y square plus z square, and dx dy dz will equal 2/3 of pi minus 1 to 1 f kappa t dt. Okay. So how to compute this? How to prove this result? The integral is over the unit ball. Okay, unit ball. And what shall we do? My idea is to convert the triple integral into iterated integral. The inner integral is a surface integral. The outer integral is a definite integral. So we apply the Euler formula. Proof. Euler formula. Euler formula says that the integral of maybe I will write yes. This is the Euler formula. The inner integral is over the surface f equal a constant t. Okay, and here you need to divide the integrand by the gradient of f. So in our this problem, the f here is just the norm of x. The norm of x. We know we already applied the Euler formula for integral over a ball. We know that B1 can be considered as the inverse of 0, 1. Here, phi x is the norm of x. Okay. Then the the partial derivative of phi is xi over the norm of x. How to know this? Maybe I will compute this again. The partial derivative of phi, that is the norm of x is the square root of x1 square plus xn square. Therefore, it is easy to see that the result is xi over the square root, that is xi over x, the norm of x. Therefore, gradient of phi is the vector whose components are the partial derivative of phi with respect to xi. Therefore, this is just x over the norm of x. Okay, this is the gradient of phi. So we know that for such phi, the gradient of phi at any x not 0 is 1. If x is 0, the function is not differentiable, no gradient. Okay, so using this result, we know that by Euler formula, the integral in the left hand side of the equality is b1 f ax plus by plus cz over x squared plus y squared plus z squared dx dy dz. This would be the integral of 0 to 1 dt or dr. Then over the sphere, over the surface, that the phi we cannot use f. Although in the Euler formula we prove we use f to denote the function, but in this example, the f here is actually this phi x, because the letter f already been used to denote the function f in the problem in our question. Therefore, we need to replace the f in the Euler formula by this phi. So the phi, the norm of the gradient of phi is 1. So the g is precisely this function. This function is the g in the Euler formula, and the gradient, the norm of the gradient on the denominator is 1. So here simply maybe x squared plus y squared plus z squared is r squared. That is the norm of x, y, z is r. Okay, the sphere of radius r, and the integrand is f ax plus by plus cz, and in this surface, in this sphere, x squared plus y squared plus z squared, square root of that is r. So this is the application of the Euler formula. We arrive at this place. Then this is the surface integral over a sphere of radius r. Of course, we want to transform this into a surface integral over a sphere of radius 1. So we make the change of variable. How to change the variable? Xc be x over r. Eta be, maybe I will write in vector form. Xc eta zeta being x over r, y over r, z over r. This transformation will transform the sphere of radius r to the unit sphere. So using this, we can write our computation 0, 1 dr. Then the inner sphere integral over the sphere of radius r becomes r squared. The unit sphere Xc square plus eta square plus zeta square is 1. Then f, the integrand become a Xc plus b eta. X is r Xc. And the r cancel with the r here on in the denominator. Therefore, we only have a c. Similarly, for by and cz, then the result is a c plus b eta plus c zeta, then d sigma. Okay, then dr. Okay. Now, by our previous example, we know that this inner surface integral can be written in the form of definite integral. Using the result of our previous example, we obtained that this is just 1 r squared multiplying 2 pi minus 1 f kappa u du. This is just the result of our previous example. Okay. Our previous example tells us that this surface integral over the unit sphere is just 2 pi multiplying this definite integral. Now, this part does not depend on r, so it can move out of the integral with respect to r. So the result is that 2 pi minus 1 f kappa u du. This is a constant multiplying the integral 0 1 r squared dr. So that is 1/3 over 2 pi minus 1 f kappa u du. So this is what we want to prove. Okay.